Hello and welcome to this video on graphing cosecant and secant with period changes and phase shifts. This is the second video, and in this video we're specifically going to focus on secant, and we'll start off with your prior knowledge on cosine of x, and I want you to notice the correlations between, in red here we have y equals cosine of x, and in blue we have secant of x. I would like you to notice that when cosine is 0, we have vertical asymptotes for secant of x. And again, this is because if cosine is 0, we have 1 over 0, which we cannot divide by 0, right? So that gives us an undefined value, which visually represents itself as an asymptote. Okay, so the other thing that you should notice about the correlation between cosine of x and its reciprocal function, secant of x, is that the maximums and the minimums correspond for the two functions. So here is how we're getting, let me get rid of these, the graph of secant of x. It's just the reciprocal values. So some connections to cosecant of x. The period is again 2 pi, and we have asymptotes that are spaced pi units apart. However, they're not at every pi. Cosecant is at every pi. The secant function has asymptotes every pi halves units times k, where k can be any integer. So at every pi half here, every pi half here, we're going to have a vertical asymptote. So this is essentially the same function as cosecant, except it is just has a phase shift of negative pi over 2. So we start backwards at negative pi over 2. And for the purposes of this video, I want you to just note that this is going to be kind of your anchor point. So if we have a period change, if we have horizontal compression or stretching, that point is kind of like your central unchanged point. And just to show you this, I have here on Desmos, let me change this, let me shift this back for you so you can see. Here we have y equals secant times b of x. So just pay attention to this point here, the anchor point that I talked about. That's going to remain unchanged. So I'll increase b, and notice I'm compressing, and that point doesn't change. The corresponding minimum does change. That'll shift. But I just want you to notice that point kind of stays the same. Okay, so I'm gonna head back over to this and shift this over. So yeah, so here's the parent function, and let's look at our first example here. So we have y equals secant of 2x, and we're again asked to identify the period and phase shift, and then sketch as much of the function as possible. So in this graph, we do have a period change. So notice our coefficient in front of our x is 2, so our 1 over b value is 2. So the period is going to be 2 pi divided by 2, which is pi. So we have a horizontal compression. Our phase shift is none. We don't have any c values inside the parentheses with the x, and we don't have any k values, vertical shifts tacked on at the end, or a multiplier in front, which would cause vertical stretch or compression. So we'll go ahead and graph this. Again, what you should note is that your parent function, the anchor point 0, 1, that's going to remain unchanged, and our period of pi is going to be split in two for a maximum and a minimum. So really, for each piece, you have a period of pi over 2, right? So this is going to be like your max, and then you're going to have a period of pi over 2 for your min. You take your period, you're going to split it in half. So that leaves us with about pi fourths on each side for my maximum. So if this is pi, again, this is going to be about pi fourths. So I can go this direction. So I'll have an asymptote here. Okay, and an asymptote here, which is really compressed. So if you have control over the units, I would maybe scale this to where you could maybe open this space up a little bit, and then another pi halves will have our other portion. So every 2 units. So here. Okay, and then this would be our minimum at -1, which is here. Okay, so we get very compressed graph. Okay, and so that is one cycle, right? And notice that the period is pi, and then we repeat ourselves. So every 2 units we'll have an asymptote, 1, 2. So another vertical asymptote here. Another vertical asymptote here. Okay, and you start to get a whole bunch of U's and upside down U's. Okay, so if we repeated this process, we would get a graph as such. Alright, so that is secant of x. Again, not much change. It's the same function as cosecant of x. Okay, just shifted back pi over 2. In this example, we had a period change of pi, so we had to horizontally compress relative to this anchor point here. And then we graph the rest. Okay, so here is a practice problem. Notice that this practice problem looks similar to the last one, except instead of a period like a compression, this one you'll have a period stretch. So please pause the video, try this one, and look back at it for some feedback. Okay, so hopefully you've had a chance to watch this video and attempt the problem. Here is the correct solution. We have again a 1 over b value of 1/2, so that's going to stretch out the period to 4 pi. It will double it. So each little piece, right, if we cut this in half, we would have 2 pi for the max, 2 pi for the minimum. So again, this point here is your anchor point. So you should have started here and said, okay, if I have 2 pi for my max, then about this way would be pi. This way would be pi. Okay, so you get your graph. Okay, and if you're not having a fun time, maybe this is you right here. Okay, so hopefully you like these videos on graphing cosecant and secant. Very straightforward, very easy. Please attempt the closure. So here is the closure. Pause the video, give this a go, and look at the feedback, and then please try your independent practice. Okay, have a great day.